And the two principal architects, there were other theorists involved that certainly helped along the way. The two principal architects was, you already know Lee Smolin, an American theorist who now works in Perimeter Institute in Canada. And I'm sure have heard of Carlo Rovelli, Italian theorist who's worked quite closely with Lee Smolin over the years. And this was all work that the two forged together in the mid-90s, towards the mid-90s. Now, as I've said, loop quantum gravity implies that space itself is quantum in nature. What does that mean? Well, here's a spin network. It's got nodes and it's got links. And what Smolin and Rovelli discovered was that the maths came out to tell them, and I'm going to give you some maths in a minute. Be ready. They realized that what was actually happening was that at the nodes, the points in this diagram, is where you find quanta of volume, the volume of space. No, I don't know either. And along the links, you'll find the quanta of area of space. The inevitable consequence of quantizing Einstein's general theory of relativity. You make space quantum in nature. Okay, so these are the quantum states of space. Now I'm waiting for a cry from the audience. I know, but Jim, but what about time? Oh, well, you see, in this road to quantum gravity, you lose time. And I don't mean that in a sense you wake up one morning and you say, what happened to the last year? Although I'm sure that does happen. I mean, time disappears from the equations. It's known as the problem of frozen time. So these quantum states of space, they're the quantum states, and so there's a sense in which they fluctuate, that they get the jitters. Something called Heisenberg's uncertainty principle means they don't stay still. They move about. However, we need to find a way to put time back into this picture. And what Smolin and Rovelli and others did was to imagine that fluctuations in the quantum states of space create the appearance of time. What happens is that as we change the number of nodes, never mind the number of links, the clock ticks. And that represents an advancement in time. So we see something like this going on. As these quantum states of space bubble and froth, we get the illusion of time emerging. I'm going to come back to this. All right. Now, again, I want to remind you that there's an important question of scale here. What I don't want you to do is to say, look, I went to the Royal Institution this evening and I had a great talk from Jim. He told us all about the quantum states of space, and I'm going to look for them. I'm going to look for them. You won't find them. For a very simple reason. Now, ignore the maths. That's area. This little guy here is called the Planck length, and it appears squared in this equation. And j into j plus 1, the square root of, is just the quantum number of space, area of space, actually. It's the Planck length that I'm interested in. The Planck length, it's called that because, in fact, it was Max Planck back in the early 20th century who realized, in fact, that with the discovery of his own constant, which is h bar here is h divided by 2 pi, Planck's constant divided by 2 pi. G is Newton's gravitational constant, and c is the speed of light. He realized that by combining these fundamental physical constants, he could come up with some fundamental units of length, time, energy, mass. Now, you can see the Planck length appears squared in this equation for area. Don't worry about the equation. It's incredibly small. The Planck length is 1.6 times 10 to the minus 33 centimeters. So that's 0.33 noughts 16. No, don't even try and think about it. The loops or networks are presumed to exist on this scale. You won't find them. Don't look for them. The Planck length is to a I did some jiggling around with scales. The Planck length is to a hydrogen atom what a large amoeba is to the Milky Way galaxy. You won't find them. A single proton contains about 10 to the power 65 quanta of volume. To all intents and purposes, a proton doesn't care. An amoeba doesn't care. The Milky Way galaxy certainly doesn't care that space is quantized at this level. So you might then have a perfectly realistic and legitimate question. So, Jim, honestly, why? I mean, why? Well, let's take the theory at face value and see what it tells us. Particle physicists love particles. Okay, that's what makes them tick. That's why they like to build ever larger colliders so they can see more particles. And it's long been thought that the force-carrying particle for gravity is this thing called a graviton. Just like the photon carries the electromagnetic force when two electrons come together, when two objects come together, they transfer gravitons between them, and that carries the force of gravity. That's what particle physicists tend to think. But loop quantum gravity says that gravitons are actually so-called pseudoparticles. They're not force particles. And to get some sense for what that means, I know that you saw in the media a few years ago these fantastic reports of gravitational waves. Remember that? Yeah. And you couldn't barely believe what the scientists were telling you, because they said, these are gravitational waves produced by two black holes merging. My God, really? But yes, so here are two black holes spinning around each other and merging. And as they do so, remember, we can detect frame dragging around the Earth. So when you're talking about massive objects like black holes, they really do mess about with the fabric of space-time, creating waves, ripples. Now, Einstein, de Broglie, remember what they said? If we can have waves, then there are associated particles with that. And those associated particles will be gravitons. So loop quantum gravity has quite a nice way of treating gravitons as, in effect, pseudoparticles, not force particles. Particles like electrons can be modeled as open loops which puncture the spin network and move around on it. So this isn't just some kind of abstract, that theory sits over there and meanwhile we get on with the good stuff. It is possible to start to bring particles from the standard model and put them onto this model of space-time from loop quantum gravity. And that's a great step forward. The theory can be used to calculate the entropy of a black hole. Don't worry about what entropy is. Anybody read Hawking's A Brief History of Time? Did you get through all the way to the end? You might remember a chapter. It was titled Black Holes Ain't So Black. It bugged him, but he realized, in fact, that black holes have an entropy, and things with an entropy have a temperature, which means they glow. Very upsetting, because how can a black hole glow? Well, it's very subtle. It's called Hawking radiation, and it's so weak that you can barely detect it above the cosmic background radiation that pervades the whole universe. But nevertheless, he was reconciled. This little equation on the right-hand side here is called the Bekenstein-Hawking formula for the entropy of a black hole. And it's really simple. Entropy is equal to area, the surface area of the black hole, divided by 4, and here's this Planck length squared again. Okay, so loop quantum gravity, remember, we have networks, spin networks. The lines, because this pervades the entire universe, remember, this is space and time. Where the lines puncture the surface of a black hole, they endow the surface with some area. Remember, the links were where we find the quanta of area. Now, you calculate the entropy not by working out how many links puncture the surface of a black hole, but how many different ways they can puncture the surface of a black hole. And that gives you a handle on the entropy. And what you get is the Bekenstein-Hawking formula. Yay. The theory eliminates singularities. Now, I haven't mentioned these yet, but the thing about general relativity is it's a continuous theory. It assumes a continuum of space and time. And theories like that, they can give rise to infinities. Things can become infinitesimally small or infinitely large. It's just in the nature of the maths. It's the nature of the beast. Penrose and Hawking, in fact, together produced various theorems in the 1970s to say that there was no way you could avoid these. If you look at the center of a black hole or at the origin point of the Big Bang origin of the universe, you'd expect to find a singularity, things that have gone infinite. Now, there's actually no such thing as infinity in nature, so something has gone wrong. But loop quantum gravity says that space-time is granular. It's got bits. I can have an ultimate unit of space, volume or area. I can't squeeze that any further. It's a bit that's like an electron, a single electron or a single photon. I can't get smaller than that. I can't divide that any smaller. And it means there can be no such thing as singularities. There has to be, if the universe collapses down or begins in a very tight, highly dense object, it cannot be a singularity because quantum nature of space won't allow that. In actual fact, what Abhay Ashtekar discovered was an intriguing possibility. We talk about the Big Bang origin of the universe, and we've got lots of evidence that suggests that that's indeed, although that evidence comes from moments after the Big Bang, by the way, not the Big Bang itself. That remains mysterious. That's when space and time were supposed to have begun. But loop quantum cosmology, the universe equivalent based on loop quantum gravity, says that there could be no singularities, and maybe, therefore, the universe began not with a bang, but a bounce. In other words, there may have been a universe before that condensed, contracted, compressed, and once it ran up against the ultimate indivisible quantum of space, it bounced. Now, make of that what you will. However,